All right, so we saw that in situations like in these, when the relevant force acting on an object is varying with time and is short-lived, it's useful to define this area under the curve, and that's called the impulse. And the impulse that the club exerts on the ball has the effect of changing the momentum of the ball, like so. Okay. So that's what we talked about. And oftentimes, so this is the impulse, that's J. Oftentimes, details of this force are unimportant, and what we're interested in is what is the average force acting on the object. So the average force is defined as the area under this rectangle is the same as this area, and that's the average force. Okay, so that would be the average force that the club exerts on the ball, and so the average force is just average force times the time over which the force acts, and that should give you the impulse. All right, now we'll consider the other situation. We'll consider situations where, so going back to Newton's second law, dp by dt, we're considering situations where this is zero, so p is constant. Okay, so again, this is net force. All net forces are internal forces plus external forces. Internal forces are always zero in a system, add up to zero. And so we'll consider situations where external forces on a system is zero. So dp by dt will be zero. That means the momentum of the system will remain constant through an event. Okay. So we'll be interested in objects colliding, for instance, and the momentum of the system before the collision will be equal to momentum of the system after the collision. All right, so that's the situation we're looking at. So here's another situation in collisions and explosions. So here's a particle, an elementary particle, and if it is at rest, this happens to decay. This particle will decay. You can look it up maybe in a millionth of a second or something. It decays into these two particles, a particle and an antiparticle. They have equal masses, exactly equal masses. So if this was at rest, when it decays, the only way it can decay for momentum conservation is these two guys have to go exactly 180 degrees apart and exactly at the same speed. Okay, there's no other way this guy can break up. If he's at rest, they have exactly the same speed and they're going in the opposite direction. Now they could go in any direction, but they will have to have the exact same speed. So that's the kind of constraints you get from conservation of momentum. Okay. Now we'll look at collisions. We'll look at collisions where in all collisions momentum is conserved, but we'll classify collisions based on whether kinetic energy is conserved or not. If the final kinetic energy is less than initial kinetic energy, it's called an inelastic collision. If the final kinetic energy is zero, this is called perfectly inelastic collision. Now this terminology is used variably. So some people say when the objects stick together, and then they call it perfectly inelastic collision, not necessarily when the final kinetic energy is zero. But anyway, so if kinetic energy is conserved, then the collision is elastic. And in an explosion, some form of internal energy, like chemical energy, is converted to kinetic energy, and those are situations where final kinetic energy is greater than initial kinetic energy. All right, so let's look at collisions. So here are two objects colliding. This is before collision and after the collide. So here's an example where they've stuck together, and after colliding, they go in that direction. I would urge you guys to go to these links and look at the simulations. So here are the classifications again. In an elastic collision, kinetic energy is conserved as well. Momentum is always conserved. And in an inelastic collision, kinetic energy is not conserved. Okay. So So we'll look at an inelastic collision, perfectly inelastic collision in one dimension. In this definition, well, here we are saying perfectly inelastic means they stick together. Okay, so here are these two objects coming at each other, colliding, and after collision they stick together and move as one. And the speed conservation of linear momentum tells us this: after they stick together, they can go only at this specific velocity, and that velocity is given by, this is the initial momentum divided by the two masses. So that's the constraint. I mean, that's the kind of power this linear conservation of momentum has. This velocity is precisely that. So now we'll look at elastic collision, where kinetic energy is conserved as well. So here are two objects coming at each other. They collide, and after they collide, they bounce off and go off. And we know that momentum has to be conserved. So this is the momentum of the two before the collision. And here's the momentum of the two after the collision. And since it's an elastic collision, kinetic energy before, kinetic energy of 1, and kinetic energy of 2 before, that's what the subscript I is, and kinetic energy after the collision is also conserved. Okay. Now here are two equations, so in problems you can ask to be solved for two unknowns. Now it turns out that with some algebra, only for this special case, for elastic 1D collisions, these two equations can be simplified. These two equations turn out to be equivalent to these two equations. This is just the same as the first equation. And the second equation, this quadratic equation, got replaced by this equation. And what this equation is telling you is V1 minus V1 initial minus V2 initial. That is the relative velocity of the two objects. And what that is, so let's say this is coming at in this direction at 10 meters per second, and this is going at 5 meters per second. Their relative velocity is 15 meters per second. So if you were sitting on this guy, he will appear to you to be coming at 15 meters per second. And that's what that is. Okay. What this is okay. So you would appear to be going at him at 15 meters per second. Okay, that's what this is. And that's equal to minus V1 final minus V2 final. And after you bounce off, you'll fly off in this direction. That guy will fly off in this direction. And to you, you're moving away at minus 15 meters per second. So that's what this is, relative velocity. So before the collision, you're going at 5 meters, 10 meters, and you are approaching him at 15 meters per second. And after the collision, you're flying off at 15 meters per second. Okay, whatever your final velocity. So that's what this is. Anyway, so in 1D elastic collision, you have the following simplification. Again, momentum is a vector, so let's consider this slightly more complicated case of a 2D collision. So here's an object colliding with this object. You can think of pool, playing pool at a glancing angle, and they they scatter off like that. Okay, so the original ball scatters off at angle theta, and this guy scatters off at phi. Okay. This is the x component of the momentum. So initial x should equal final x, initial y should equal final y. And that's what these two equations are. And in addition, if kinetic energy is conserved, then this should be true as well. And so now you have three equations at your disposal, and you can solve problems with three unknowns. All right, let's pause now.